credential session. And our first speaker is going to be Corentin Judy. And he's going to tell us about how to build a lattice-based signature with efficient protocols and how to apply this to anonymous credential.
Thank you for the introduction. I'm just going to check that. Okay, the slides are fine. And I can, yeah, okay. Thank you for the introduction. Hello, everyone. Thank you for attending this session. Today, I want to present a joint work with Adeline Roux-Langlois and Olivier Saunders on a lattice signature with efficient protocols, which is a primitive that is very interesting in the design of signatures for privacy, essentially, and how we can use those signature with efficient protocols to derive anonymous credential systems. So I'm going to first focus on the signature with efficient protocols, and we'll conclude the talk with the anonymous credentials part. But first, let's do a quick reminder on regular signature schemes. In a regular signature, you have three parties, user, signer, and verifiers, and two workflows interacting between them, one for obtaining signatures and one for authenticating into a system. So in the first workflow, the user will send some data, which I'm also going to call the message or attributes, to the signer, and the signer will use its secret key to produce a signature certifying this data for the user. Now the user holds the message and the signature and can send both to some verifiers, which can publicly check that the signature is valid to allow the user to authenticate into a system. But as you can see, this is not very suited for privacy applications because in that context, we want to hide as much information as possible. And here, both the message and the signature have to be revealed at some point in the process, so we would like to hide those. Fortunately, in 2001, Kamenish and Nizanskaya introduced a primitive called signature with efficient protocols, which sets out to address those exact issues. So we're going to change this picture by first looking at the issuance process. And instead of sending the message in the clear, we're going to use a cryptographic commitment scheme to commit to the message and only send the commitment to the signer, as well as prove that the commitment is well-formed. And now the signer can once again use their secret key to produce a signature, but on the message that is hidden inside the commitment. So this already places a big constraint between the signature and commitment scheme so that from the commitment alone, I can generate a signature on the message hidden inside it. So kind of a blind signature process. But then we have a user with a signature on its message. And now instead of sending both to the verifiers, they will produce a zero-knowledge proof of the verification algorithm of the signature scheme by basically showing that they know a valid certificate on their data without revealing either to the verifiers. And so now the verifiers can once again publicly verify this proof and make sure that the user is allowed to authenticate into the system. And now we also have a big constraint coming out of this is that the signature verification must be provable in zero knowledge. So this already discards like random oracle-based signature schemes because the random oracle will not interact well with zero knowledge proofs. So assuming we have these constraints met, we have managed to hide all the information we wanted in the signing process and also in the verification process. So from this nice theoretical construction, what can we do with this in the privacy world? And the answer is a lot of things. The most straightforward one is anonymous credentials, because it perfectly matches the picture that I presented before, where we have a user who wants to obtain signatures on hidden messages and then prove possession of this credential to some verifiers, to some organization in an unlinkable manner. So this is exactly what we presented before. You can also do blind signatures, which are essentially a relaxed version of anonymous credentials, where you're allowed to divulge the message during verification. And you can also do plenty of other things like group signatures, e-cash, e-voting systems, and so on. But although it's already very interesting from a theoretical standpoint, it also has direct industrial applications. For example, we have enhanced privacy identification and direct anonymous attestation, which are kind of flavors of group signatures. which can be designed from SCP schemes and that are currently deployed in billions of devices like trusted platform modules, SGX enclaves, and so on. So having those systems run smoothly needs very efficient EPID and DAA, which in turn mean we need very efficient SCP schemes. So the next question is, do we know how to construct SCPs and are they efficient? The answer to both questions is yes. In the classical setting, we have very efficient instantiation of SCPs. The first ones based on the strong RSA assumption, and then later ones which have greatly improved over the years based on pairing-friendly groups. And these leads to very efficient group signatures, anonymous credentials, and all of the things that I presented before. And as a frame of reference, the best group signature to date, which is standardized at ISO, is based on an SCP scheme, and its size is 0.16 kilobytes. So if you compare to a regular CDSH signature, which is 64 bytes, it's only 3 times as big. So it's extremely efficient. The problem, though, with all of these constructions is that they all rely on assumptions that do not withstand quantum computing. So the next question I want to ask is, do we know any post-quantum solutions, any SCP scheme that would be secure against quantum adversaries? And once again, the answer is yes, but in a slightly unsatisfactory manner, in the sense that there is, prior to our work, only one proposal of post-quantum SCP based on standard lattices from Lieber and his co-authors in 2016, but it's rather a proof of concept than anything else because they adopt a rather asymptotic parameter and security analysis, which when you plug parameters to achieve a security target like 128 bits of security, you end up with those kind of sizes. So very intractable, not usable in practice at all in terms of key sizes, also very large signatures, and the verification proof size is also extremely big, which is one of the main metrics that we want to optimize over. And so what I want to present today is a simpler, more compact, and more efficient construction of post-quantum SCP based on standard lattices, but that also extend to structured lattices for more efficiency. And in the structured case, we end up with those efficiency estimates, which are very much improved over the 2016 construction by several orders of magnitudes, so on all metrics. Okay, so now I want to go a little bit under the hood and describe our construction in more details. But right now, we're just going to focus on the signature scheme. So forget about those two workflows. Of course, we're going to keep them in mind to make them interact with commitment and zero knowledge. But right now, it's just a signature scheme. And a couple notions that I'm going to need. The first one is the main security assumption that we make for the security of our signature. It's the modulo SIS assumption, which says that for a uniformly random matrix A, it is hard to find a short non-zero vector X that verifies AX equals 0 mod Q. So this is a rather standard assumption in Lattice crypto, and this is the only one that we need for the security of our scheme. And I'm also going to need for the next couple of slides the notion of trapdoor on a matrix A. And so a trapdoor is some piece of information. I'm not saying what exactly because it changes depending on the context. A piece of information that I can use to sample Gaussian vectors X that verifies AX equals U mod Q for any syndrome U that I decide. All right. Okay, so now I'm going to describe our signature, and the way that I want to present it is rather different from how it's presented in the paper. I want to start from the 2016 construction and identify the main sources of inefficiencies and see what kind of other design choices we can make to make it more compact. So here is the 2016 construction, at least its verification equation. And I'm going to describe how it works. So all the elements in black in the equation are part of the public key or public commitment parameters. The elements in orange are the signature. So we have tag bits, tau i's, 256 of them for security reasons, and two short vectors, V and R, which are the pre-image sampling V and the commitment parameters R. And then we have the messages, which is composed of binary vectors, MJs, And what I call this MJ1 minus MJ on the right is the concatenation of the binary vector MJ and its binary complement. Okay, this is just going to be important in the next argument. And of course, the signer holds a trapdoor TA, which is secret, on the first matrix A, but that can also be extended to the full matrix. All right, so how does it work? The signer first select random tag bits, tau-i's. Then we go on the right-hand side. The signer will commit to the message by selecting a short R, computing D0R plus the sum of DJ MJ1 minus MJ. Take the binary decomposition of this commitment, multiply it by D, add U, and then use their secret trapdoor to find a short vector V that concludes the relation. Now let's look at why it is inefficient. The first thing that I briefly mentioned is this MJ1 minus MJ. Virtually what it does is that it kind of doubles the message size, which is not so concerning because we have a succinct commitment. But the problem is that this specific structure needs to be proven in zero knowledge when we're going to perform the zero knowledge proof of verification. We have to prove that the message has this specific form in the signature. So this already complexified a little bit the zero knowledge statement. The second thing, which is a little bit more concerning, is this binary decomposition of the commitment. The reason why it is concerning is because in lattice zero knowledge proof, what we're able to prove is linear and quadratic relations, and norm constraints. And the binary decomposition is neither of those things. Fortunately, what saves this construction is that the binary recomposition is linear. So what we would do to prove this statement in zero knowledge is define this binary decomposition as an intermediate witness, W, then prove that this whole matrix times V equals U plus DW, prove that the binary recomposition of W is equal to the commitment, and then prove that W is binary. But we have all these intermediate steps which essentially deteriorate the zero knowledge argument and in turn the proof size. So now we need to see why those arguments are necessary. And actually, there are only design choices made for the security proof, and they're only used once in the security proof. So an important part of our work was to try and find new arguments, new security arguments to get rid of these constraints altogether, and in the end, get rid of these inefficiencies. So I'm going to skip the details. All of it is in the paper, but we managed to get rid of these constraints. And now we have a much cleaner equation that can directly be proven in zero knowledge, but it's still rather not compact. The reason for that is because we still have those tau-i's AI's. And as I said, we have 256 tag bits, meaning that we have 256 fully random matrices AI's in the public key. So either you represent them as seeds if you want to compact the public key, but then you still have to recompute them in the signing process. So it turns out to be inefficient either way. So to get rid of this uncompactness, if you will, we actually just replace the notion of trapdoor that we're going to use and use a much more compact trapdoor, which is based on gadgets. So now, instead of having 256 matrices, we have two matrices, A and A times R, which are part of the public key. The tag is changed to a scalar, tau, and the G matrix is just basically the binary recomposition matrix, which is the way those preimages are sampled. So now we have much more compact keys, and we can actually go a little bit further than this. Because right now, by changing this notion of trapdoor, our trapdoor is just a short matrix R, which is completely independent of the matrix A. And whereas before we had TA, which inherently dependent on A. But right now, since it's independent, we can reuse the matrix A as being fully uniformly random, and as such, being used as part of the commitment matrices that is used to hide the message in D1M. So this is why before we had this D0R, and now we reuse the matrix A at this stage to allow for a more compact construction. And the reason for that is because we can now merge the commitment randomness R to the first part of our vector V. So what it does is that instead of having to send two vectors of roughly the same norm as part of the signature, we only have one, V'1 here, which is 2 times as big. But in terms of bit size, it means that we only add 1 bit per coefficient. So it's much more compact for the signature part, and also for the zero knowledge part, because we have one fewer vector to prove knowledge of. So in lattice-based zero knowledge, it's always better to prove knowledge of lower dimensional vectors with kind of higher norms than the opposite. So in the end, we gain on the signature and the proof size at the same time. All right, so this is basically it for our signature scheme. It's a rather simple construction, but it's much more compact than what we had before. Okay, so now let's see how we can plug the signature into our 2 different workflows and see how to design those anonymous credentials that we talked about at the beginning. And for that, we're going to go back to our protocols, so the issuance and the showing or verification protocol. And the one thing that we observe in our signature scheme, and also in the prior actually, is that the signing key is only used once the commitment has been computed. So we can actually delegate this commitment step to the user and allow the secret key to be used only once the commitment has been sent by the user. So the user commits to the message, error plus DM, provide a proof that it's well-formed, sends it to the signer who can check the validity of this proof. Then it selects a tag and use their secret key to find this short vector V that verifies the relation, sends it to the user, and the user can then merge the commitment randomness on their own to the first part of the vector V, obtaining the full signature. So this is rather straightforward. There are a few subtleties that I decided to hide here, but all the details are in the paper if you're interested. And then for the showing or authentication protocol, then it's simply providing a zero knowledge proof of the verification algorithm. And we made it so that the verification was a quadratic relation directly provable using the latest framework from crypto of last year. So this is just generating a zero knowledge proof and checking that it is valid using public parameters. Okay, so this is basically it for the anonymous credentials construction. Now, just a quick word on its security. We expect several properties. The first one is anonymity, which means that we do not want any leakage on the message or the signature, or at least everything that we want to hide in the process. So depending on the construction, like blind signatures or group signatures, you have different requirements. But if you want to hide everything, relying on the hiding property of the commitment scheme and on the zero knowledge property of the different proof systems, then you can ensure anonymity. Also, one thing that is not on the slide is that we expect unlinkability, meaning that between different interactions of verifications, I do not want to be linked between those interactions. And for that, because we use zero knowledge proofs, and each time we produce a fresh zero knowledge proof, we remain unlinkable in the process. And lastly, for unforgeability, we need to prevent ourselves from 3 types of forgeries. The first one I'm not going to talk about because it's in the details that I decided to omit. Second one is against malicious provers, where the attacker would try to trick the verifiers in the zero knowledge argument, but based on the soundness of the proof system, this only happens with negligible probability. And finally, we have, of course, fresh signature forgeries, but based on the EU FCMA security or signature scheme, which is reduced to modulo SIS, this does not happen either. Okay, so this is basically the end of my talk. Just to wrap things up, what we provided is a more practical construction of lattice signature with efficient protocols from structured lattice assumptions that is much more efficient than the only prior construction from 2016. And this also provided the first explicit lattice-based and post-quantum anonymous credentials system. And for the second one, you just have to wait 5 minutes for the next talk. where Khan will present their scheme. So just a quick word on this. They achieve a much more compact construction in terms of credential size, public key size, and so on, but they rely on a rather new assumption, whereas for us, we only rely on standard assumption like modulo SIS, modulo LWE, which have been around for a few decades now. So I will let Khan give you all the details. So thank you for your attention, and I'm happy to take any questions.
Thank you so much, Corentin. Do we have any question from the room or from Zoom? So I have a question.
Yeah.
In the state of the art, you are comparing with the LLM.
Mm-hmm.
And my question is, was there something else maybe based on hash functions, or really the only post-quantum safe ones that we knew was LLM?
Not to our knowledge. To our knowledge, there was only this lattice construction. We also tried to look into codes, see if there was signature with efficient protocols, but there wasn't. So we originally started from this 2016 construction and tried to, as I said, tried to see if we could make it better in some way.
Okay.
Yeah.
Okay, interesting. So, well, so then it's open to do it with hash functions, maybe, or we don't know.
Yeah, I guess so. Yeah. Okay. As I said, to my knowledge, there is only 2 construction, or now a few more, but they're all based somewhat on lattices. For post-quantum construction. The difference, though, with our construction and the next one is that ours is really focused on this signature with efficient protocols and not just anonymous credentials. So it can lead to a variety of different privacy-enhancing applications, as I mentioned at the beginning. By just a few tweaks, you can obtain group signatures, or if you relax a little bit the anonymous credentials, you can have blind signatures, which may be a little bit more efficient. But yeah, all of that for now is based on lattices, and yeah.
Nice. Thank you. Yeah, I don't see more questions, not even from Zoom. So let's thank the speaker again.
Thanks.
I'm gonna wait a minute. I'm gonna wait a minute because we are a bit, we still have time. All right, our next talk is by Khan Nguyen, and he's also going to tell us more about how to build anonymous credential, practical anonymous credential from lattices.
Mic check, good. So yeah, thank you very much for the introduction, and thanks Khan for the sneak peek. So hi everyone, my name is Khan, and I will talk about the framework for practical anonymous credentials from lattices, which, as was hinted before, will use like a new assumption. So please feel free to break it quickly so that we can finish the talk earlier. So this is joint work with Jonathan Butel, Vadim Lubashevsky, and Alessandra Scafuro. Okay, let's see if it's working. Oh, no. Okay, so we already had the background on anonymous credentials, but for those who just joined us, we have three parties: the issuer, the user, and the verifier. And the user has some public and private attributes. So maybe the private ones are the date of birth or the address. And the user wants to obtain the credential from the issuer. And then later, the user wants to prove possession of the valid credential to the verifier. And yeah, there are some properties which were discussed before, like the private attributes should be private, and also unlinkability. So even the issuer, anyone, they can't link the credential to where it's used. So yeah, so we discussed, well, we already saw that there's a common framework to build such primitives, which contains the following ingredients. So it has a signature scheme, which is used for the issuer to kind of sign these attributes. And then there's a zero knowledge proof, which appears in two places. So the first one is when the user wants to prove some properties of the private attributes. For example, the age is more than 21. And also in the second part where the user wants to prove possession of the signature. And then the third one is the commitment scheme, which can be used along with the zero knowledge proof. So yeah, so there is a name like the signatures with efficient protocols, and also there's a recent work which kind of in a similar flavor, which is like commit transferable signatures. Okay, so if the goal is okay, let's just build the most efficient anonymous credential or signatures with efficient protocols, then let's just instantiate all the best. If we just take each ingredient, we take the best available like construction and just mix them, right? And then, yeah, so let's try this. So let's start with the signature scheme. So we look at the NIST standardized constructions from lattices. So for example, okay, let's start with the lithium, which is basically like the lattice adaptation of Schnorr. So we have some signatures, the sigma protocol for proving a simple lattice statement. So AS is equal to T mod Q, where A is a matrix, S and T are vectors, and S is short. And then to make it, to transform it into a signature, we make it non-interactive using the Fiat-Chemie transform, and we put the message in the hash function. Okay, and then we have the second construction of the Falcon, which is based on the GPV framework. So basically, given the trapdoor T for the matrix A, which allows us to sample short pre-images, well, the signing process, the signing algorithm samples short S such that AS is equal to the hash of the random salt and the message, and the signature is the pair RS. Okay, great. So just take the first ingredient and we are 33% done, right? Well, we need to mix it with a zero knowledge proof. So can we provide a zero knowledge proof, of possession of a signature in this case? Well, as it was described in the previous talk, it is a bit problematic, right? Because there is the hash function inside. And there are kind of two issues. So the first one, a little bit more from the efficiency point of view, is that if we instantiate it with our favorite hash function, then basically the goal boils down to proving the hash function evaluation. And then, we have to look at the hash function as a circuit and then reduce it to our favorite language and use a proof system or snark and so on. So we think that if we, focus on this approach, then we shouldn't, in the long run, maybe we shouldn't get better sizes. But compared to like 200 kilobytes, maybe it's possible. But it would be nice to have a construction which doesn't use all this heavy machinery. And the second thing, maybe from a theoretical point of view, we can see that there is kind of a mismatch between, between the security of the signature and the zero knowledge proof, because in both of these schemes, the unforgeability is in the random oracle model. So the hash function is a random oracle. So in this case, either we need to prove the statements related to random oracles, good luck with that, or we just need to instantiate the we have to argue that unforgeability lies in the random, is secure in the random oracle model, and then we heuristically assume that it's secure under when we instantiate the random oracle with a particular hash function, and then we use the zero knowledge proof on that. So there are a few subtleties, as we can see. So what we discussed, what we kind of focus on in this paper is, okay, so what happens if we want to swap this hash function with something, I call it a ZK-friendly function, meaning that we can prove the function evaluation or the pre-image of the function in zero knowledge, like in a easy way. So for the lithium, well, it's there's probably not much hope because we need the random oracle to do rewinding and do the forking lemma and so on. So we believe there is much more hope in the GPV framework. So then we're moving to the basically the core, or like the crucial observation of this signature scheme is that, given the oracle, which basically this is a signing query, signing oracle. So it's given any message X. I will remove the salt for now. It generates a short vector S such that AS is equal to H of X. And then outputs the, let's say, the S and H of X. So this oracle in the security proof can be simulated because, well, we can just rearrange certain steps, and we can first sample a short S, set AS to be equal to Y, and then program H of X to be Y. And here we are using certain techniques from lattices, but basically that's kind of the crucial observation for the security proof, that we can simulate that oracle. And now, well, the main motivation was, okay, so what if H is not a random oracle, but some function? So now the question, kind of a related question, now becomes, okay, if we are given an oracle that, given some message X from the set M, generates a short vector S such that AS is equal to some function f of X, and outputs the S, then is this useful for generating a new pair S star X star, such that S star is short and X star belongs to that message space M, such that AS star is equal to f of X star? Well, I mean, I cheated a bit because I removed the salt, and now it would be useful because we could just run this oracle twice on the same input, and then we subtract two equations and we get a short solution for A. So what I should say is that given an oracle that generates a random X in some set M, it generates a short vector S such that AS is equal to f of X, and then outputs S and X. So is this oracle useful for generating a new pair S star X star, where S star is short and X star is in the message space, such that AS star is equal to f of X star? And our main goal was to instantiate that F with some, simple functions, so that we can prove, pre-image in zero knowledge efficiently. So what we focus on is, okay, let's just pick F to be a linear function. And it seems a bit dangerous, right? Because if I just run the oracle twice, then I get AS1 is equal to f of X1. AS2 is equal to f of X2. So I can just sum them and I get a new pair, right? And S1 plus S2 is small. But here comes the difficulty, that X1 plus X2 may not be in that set M. Okay? And also another thing is that S1 can be small, like S1 is the norm of S1 is at most B, norm of S2 is the most B, but when you sum them up, then is the norm of S1 and plus S2 still less than B? So to instantiate that, we focus on a very simple instantiation. So F is an identity function. So basically nothing happens, but the M is the set of binary vectors. So now, well, if I get the random vector X1 and random binary vector X1 and random binary vector X2, then, if I sum them, then with low probability, the sum is also a binary vector. And sure, maybe you can, from the cryptanalysis point of view, one can try to find a short linear combination for which the resulting X star will be a binary vector. But then if I look at the corresponding pre-image, it may have large norm. Okay, so kind of there are two difficulties in this kind of problem. So the first one is trying to, let me just stick to this instantiation. So the one difficulty is that we're given many X's, many random vectors, and then the goal is to find, maybe we can try to do linear combination, but then with some effort, maybe we can get another binary vector, but then the corresponding pre-image must be small. So there are kind of two difficulties. So the first one is keeping the condition to be in the set M. in this case, around binary vectors, and the second one is on shortness. So yeah, so this is our new assumption, the ISSF assumption. So yeah, so given an oracle that generates a random X in the set M, so just think of it as binary vectors, it generates a short S such that AS is equal to f of X, outputs S and X. And the goal is to find a new pair S star X star, where S star is short and X star belongs to the set M such that AS star is equal to f of X star. Okay, so that's the assumption. So feel free to break it, but for those who decide not to, good decision. We will move on to constructing the signature scheme out of it, because it's not obvious how one can build a signature scheme from that. And the signature scheme is basically that we have the random matrices A and B, along with the trapdoor for A, trapdoor T for A. And then to sign, we pick a random X, and we use the trapdoor to sample a short vector S such that AS is equal to f of X. So kind of the same as before, but now we are also adding B times plus B times M. And the signature is S and X. Then to verify, we just check the equation, and okay, so that's the old version of the slide. And S is short, and also the X is in the set M. Okay. So yeah, so one can think of this modification as, well, we are adding B times M here, right? Oh, no. Wait, where am I? Oh, that's the old one. Oh. Okay, let's see. Can I go back? Yeah, so one can think of this signature, at least the term B times M, as the commitment to M. So that's kind of the standard sys commitment. And well, yeah, so this means that informally we sign on the commitment. So this means that if we want to have an anonymous credential, then we can think of the user sending the commitment to the M, which contains the attributes, maybe some randomness to make it hiding. It sends the commitment BM, and then the issuer will run the signing algorithm to output the credential. So now, because this is this is like an old version, I need to like skip 10 slides. So the next slides will, okay, so let me see. Yeah, so maybe I'll spend a few minutes on the unforgeability proof. So basically so now to prove unforgeability, so we're given access to this oracle, which gives, well, we just create signatures. So basically it's, given a low norm vector M, generates a random X and outputs or samples a short S such that AS is equal to f of X plus BM. And now the goal is to find a new M star along with the S star X star such that S star is short, X star belongs to that space M, and AS star is equal to f of X star plus BM star. So the general idea is that, okay, I discussed what the role of the matrix B is. It is kind of the commitment key, but it's also useful because in the proof, we can swap B with A times R, where R is short. So then I will swap all the places where there is B with AR. And it's nice because then in the equation in step 3, I have A times S minus RM is equal to f of X. And this is where we reduce unforgeability of the scheme to the ISSF problem. Because, okay, let me just, yeah, because then we can just ask the ISSF oracle for a new instance, and we get the S bar and X, and then I can just write S to be equal to S bar plus RM. Okay, but there is a mismatch between the distributions, which I won't go into the details, and also because the slides are old. Oh, so that's it. Oh yeah, so in order to kind of fix this mismatch between the distributions, we will use rejection sampling over lattices. So that's kind of the main intuition on the unforgeability proof. So this is like old, so let's just switch to this. So yeah, so that's how, and okay, so now we're constructing anonymous credentials. which follows the similar framework as before, but we just use this different signature scheme. So now we have, let's say we have a vector C, which contains the attributes. It's a small norm vector, contains attributes and randomness to make the commitment hiding. And then we send T equal to B times C. And then also the proof that pi1 is of the right form, that T is of the right form. And then the issuer checks the proof and then runs the signing protocol, which is basically picking random X from the set M and then using the trapdoor to compute the short vector S such that AS is equal to f of X plus T. And just to recall again, well, the T is indeed equal to BC. So this is the kind of the similarity to the underlying signature scheme. And then the issuer outputs the pair SX. And suppose we want to reveal C1, but keep C2 secret, let's say the date of birth and the address. So then the user gives a zero knowledge proof by 2 of correct the credential S and X and also the C2 such that AS is equal to BC, which is now I split into B1 C1 plus B2 C2 plus f of X. So the motivation of the whole, basically like of the whole presentation was to make this proof pi2 as efficient as possible. And to do that, we take a function f for which we can prove preimage efficiently. So in this particular case, we have to prove that X belongs to that set M. And in the concrete case, we want to prove that X is binary for which we can prove efficiently. So yeah, so in terms of ingredients, we're using the ISSF signature scheme. For the zero knowledge proof, we are using the LNP framework from last year, and the commitment scheme is the standard sys commitment. Yeah, so we reduced. So maybe one very briefly about security proof. So well, we reduced unforgeability of the signature scheme, of the anonymous credential to unforgeability of the signature scheme, which I also call this the interactive ISSF, which was also mentioned in the previous slide. And the proof is kind of complicated because of various extraction difficulties, but we will skip that for the purposes of this talk. So yeah, but like we can see that the adversary sends as a user, it sends the first message T and pi1, and then if we assume that pi1 is straight line extractable, then we can get the attribute C, for which we can call the interactive ISSF oracle to obtain the credential SX for which we pass. But then there are also like there's also rewinding for pi2, so there are like a lot of complicated stuff. So the reported sizes here are not the same as in the previous slide because so the reported sizes are like 2 times bigger in the previous talk. And here we are kind of we are being very, very optimistic because in the security proofs there are various artifacts of the proof to make it secure, but it doesn't make it maybe not to make it secure, but to make the proof work. But there are a lot of steps in the there are a lot of steps in the proof which are just artifact of the just to make the proof work. But it doesn't mean that it's secure if we remove some parts. So this is like very I would say very optimistic. And in the final version of the slides, I wanted to include the bigger ones. But so this is what it is. And in terms of the future work, well, the interesting question is about this new assumption, right? This ISSF. And the interesting question is like, what are the candidates for instantiating this function or this set M, such that, so on the one hand, we want to, well, at least understand if it's secure for certain instantiations, but at the same time, we want the F to be kind of easy enough so that we can prove zero knowledge efficiently. And also, we don't restrict ourselves to just sys or LWE, but maybe with non-standard assumptions, maybe like with this one, we can get more complex primitives, maybe like aggregate signatures and so on. So I think this is a very exciting research direction. And yeah, that concludes my talk. Thank you.
Do we have questions? Yes.
Thanks for the talk. You mentioned that part of the extraction is straight line and part of it is rewinding. Could you comment on that distinction?
Yeah. So in that interactive step where we have the okay. So yeah, when the adversary sends the first message to the issuer, then to kind of not to deal with the problems with with various extractions, we just use a straight line to extract the attributes directly from the proof.
Okay, so the attributes are straight line extracted,
Like
but
this first proof pi1 is straight line. Yeah.
I see. And the second proof is rewinding.
Yeah.
Why the second proof rewinding and the first?
Well, if we for some people, the end product is this credential pi2, and that's where we want the most efficiency. Obviously, the communication is also important, but maybe there is more leeway if we make the pi1 less efficient, but pi2 more efficient.
I see. Thank you.
Thanks. It was very interesting. I have a question on the candidates for F.
Yeah.
Is there any requirement of linearity, or will any function that you can efficiently like prove knowledge of a pre-image or something, can you just drop it in and
Yeah, so I mean, it doesn't have to be a linear function. We are also trying to work out some instantiations where F has some tensor structure, so it's not very linear, so it's not easily broken. But yeah, the most important, I mean, there are two important aspects. The first one, it should be secure, I guess, and the second one is that your proof system that you want to use, it should support kind of efficient proof of pre-image of F.
Thanks.
Thanks for the talk. I have one more question. So could you replace the random oracle using some cut and choose approach?
That would be in the place in the signature type, right? Like in the signature. Yeah, to be fair, we didn't think about this, but yeah, if we can prove the zero knowledge proof should support that, but maybe, yeah, maybe it should be it's also another direction. Yeah.
Okay, thank you.
All right, so thank you so much, Ken, for your nice talk. Our speaker is Betul Durak, and she's going to tell us about anonymous tokens with the stronger metadata bit hiding from algebraic max.
Thank you for the introduction. Hello, everyone. My name is Betul Durak from Microsoft Research, and today I'm going to talk about the lightweight version of anonymous credentials in the last talk of the session. So I'm going to start right away with the motivation and application. And the widely known application of this anonymous tokens, one-time anonymous tokens, is the privacy pass. Probably you have heard of it. And it's a client-server setting. The idea here is that the server would like to host some services, and would like to give control the access on this service through some tokens. And they want some kind of security and privacy properties of these tokens, and that's why we have this protocol that I will describe now. So the protocol has two phases. In the first phase, the client goes to the server and requests some tokens, and then the server issues some unforgeable tokens, where unforgeability is the security property of the protocol. And the second phase is the showing phase or redemption phase, where the client goes back to the server at another time to redeem the tokens. And if the tokens are valid, the server gives access to the client. So the privacy property that we want from this protocol is the unlinkability between the issuance session and the redemption session. So one instantiation of such a protocol could be done with some private key primitives, because in here the server behaves both as an issuer and a redeemer. And indeed, in the privacy path, this primitive is oblivious PRF. So, but I skipped the maybe important part of this protocol, which is the trust establishment between the client and the server. Obviously, server will not issue tokens to everyone who requests it. There should be some kind of trust establishment between client and server. So it's a huge problem in itself, so I'm not going to get into too much details, but the one example is where privacy path actually captures is using the CAPTCHA to trust the client. If the client can solve some kind of CAPTCHA, it's I think a good enough signal for the server to believe that it's a human, it's not a bot, but there are various problems here. So the state of the art currently, as far as I know, is to use some kind of machine learning to decide if the client is trustworthy. And in here, I kind of throw a heavy hammer machine learning, but really sometimes it can be very simple statistical analysis, like the server creating some kind of distribution and seeing if the client is going to fit in this distribution or not. So now let's go back to the protocol again, and now knowing that the client might be malicious, the protocol will change a little bit. So any client can go to get some tokens now from the server, and then what server will do is to decide with these tools, the statistical tools that it developed to decide if they want to give the token with an embedded bit inside it. So the reason that it doesn't reject immediately if the server thinks that the client is malicious is the kind of the tension between the privacy and security, because it kind of gives client some signals, and the client can learn that the server can detect the behavior and it can adapt the strategy accordingly, not to be caught next time. So this is called a deferred rejection. The idea again is to give the token no matter what the decision on the server side is, but with an embedded bit. And when the client comes back with those tokens, which the client does not know what is inside this token, the bit is hidden, and the server will accept if the embedded bit is 1. And that's why the primitive's name is the anonymous tokens with hidden metadata bit. So we are not the first one working on this problem. There was a work in 2020 in the presented here in crypto. Its name is private metadata bit token, PMBT in short. I'm going to introduce the interface and the protocol a little bit, and then describe why we might do better than what PMBT was proposing. So the interface is there's a setup and key gen. It's a CRS model. The key generation outputs some public parameters and the key for the server. And there is the protocol between the client and server is that it starts with the client query, which inputs a tag T, which inputs a tag T and the public parameters, and then it outputs a state for itself and the query which will go to the server, and the server will run the issue token algorithm along with its secret key and the hidden bit B from the client, and then it will return the response to the client. Finally, the client will use the state that it's stored to finalize the protocol to come up with to conclude it with the tag T and the quote unquote signature on this T with sigma. So there are two other this is for the issuance. This entire protocol over here, the issuance protocol. For the redemption, there are two algorithms which is defined. The first one is the verify algorithm, which takes the input of secret key and the token itself with the tag and the quote unquote signature on it, and it returns a true or false. And then another interface which is called read bit, exactly taking the same inputs but returning 0, 1 or an error. So here is where our confusion starts, because this essentially gives us two different notions of validity of the tokens. So I don't understand fully like what validity of a token would mean in this case. Would it mean that the verify returns true, that indicates that the token is valid and well-formed, or the read bit is returning a bit means that it is a valid, or even there could be some other notions of validity or well-formedness of these tokens. So that's the one thing, the first to start with, the point that might be a little bit confusing. So this is why we want to understand a little more on the protocol now. So I'm not going to get into the details of the protocol itself, but what I will describe here is there are secret key, which is actually a pair, and depending on the bit that the server wants to embed, it uses either the X0Y0 or X1Y1, or here, as I show here, XP, YB pair will be used for issuing the tokens. And when they're doing the redemption, it's just checking which pair of the secret key satisfies the equations, and accordingly it returns the bit, or it returns an error. And I introduced, as I mentioned before, there is another interface, another algorithm in the interface, which is the verify algorithm, and the protocol implements this algorithm as returning always true. So again, the same question: does that mean that all the tokens that are formed are valid or not, or should we look at the read bit algorithm? So before getting more into the why this is a problem in the security notions, I would like to pause a little bit to say like a little bit about the cryptographic primitives here used in the privacy pass and the PMBT. It's a oblivious PRF, essentially just like an extension to the privacy pass, and the same philosophy is used. The input tag is only input by the client. Server has nothing to do with this tag generation, and the security properties, including the one-more unforgeability and unlinkability. And because of the hidden metadata bit, it is also privacy of the metadata bit as a security notion we need to define. So that's the PMB privacy of the metadata bit part is where I will focus on this talk. The definition of PMB is as follows. So in here, the adversary is the client, and we are trying to hide the bit, challenge bit B star from the client. And the adversary, the client, has access to 3 different oracles. The first oracle is the O-sign oracle, where the adversary actually has a big power. He can even choose the bit that the oracle needs to embed inside the token issuance part in the issue token algorithm, and it returns the bit, the response, by using the bit and the query which is given by the adversary. So if you're not familiar with this type of protocols, you can think of it, I can make the analogy to the encryption mechanisms. This is actually very similar to the CPA security with the chosen plain text attacks. So you can imagine that this B over here is the plain text that this oracle will encrypt and return a response with. So this is very, very similar. And now we can look at the challenge oracle, where the adversary will just give the query the oracle with the query input query, and then it will get a response where the challenge oracle embedded the challenge bit B star in here. And the adversary's job is to distinguish between B star being 0 or 1. So far, so good. This is really analogous to the CPA security. And now if we want to make it CCA-like security, can we do that in this setting? Well, the answer is essentially no, because of the unlinkability properties we have. If we had the decryption oracle, quote unquote, what would happen is that the adversary would come with some kind of tokens, and the oracle would need to decrypt it. But because of unlinkability, the adversary has no clue if the query comes from, if the token comes from the challenge oracle, or it comes from the encryption oracle, or it has no clue. There is an unlinkability that the server cannot actually return this, cannot implement the decryption oracle. So the next best thing that we can do is to implement some kind of a verify oracle. So what verify oracle does is that at least when the adversary inputs a token T and sigma, it can return if this tag is, if this token is well formed or not. So this is the best we can do. But unfortunately, as you see here, the oracle is instantiated with the verify algorithm. And as I showed before, the verify algorithm always returns true. So essentially, there is no real meaning of using this using this as an oracle to check if there is a well-formed, if adversary cannot check if it is a well-formed token or not. And if this was implemented properly, what I would describe now would be a problem, but it is not, because the verify always returns true. There is no really meaningful decryption, quote unquote, oracle here. So what would be the problem if this was a true, like, well-defined the CCA secure notion? The adversary would make two queries. The first one is going to be the all-sign oracle. It will be essentially asking for a signature on a tag T1, small T1 here, with the bit 0. Let's say bit 1 is the query bit is 0, and the oracle will compute this tag, which is not, it doesn't matter how the computation is done here essentially, but in the second query, the adversary will query the challenge oracle with this new differently formed tag. So in here, it will use a new tag T star, and then it will also use the T1 from the previous session by subtracting them. And it is because it is supposed to be oblivious to the server, so the server will not know what is this, how this is formed, and it will just decide to answer. It will just answer by using the B star, which is the challenge bit in the response. So what happens here is that if we had a true notion of validity, the adversary would be able to go back to the server to redeem the token T star and the sigma, which is formed with C star, S star S1 and W star W1 here. And if the validity oracle was returning, yes, it is a valid token, the adversary would very easily infer that the challenge bit is B0, B star is equal to 0. And this comes from the fact that there is this linear operations that is happening. And if the bits are matching, that is easy to infer that it is indeed the 0 bit which was used in the first query. And if it was not well-formed token, then the adversary would infer that it is B star is 1. So this is the type of attacks that we would like to avoid. And if the question is that if we can do that and how we can do that, and what to start with, what is the problem to solve first. So the first thing that we identified is that essentially these oblivious PRFs are deterministic primitives, right? And what we are trying to do, or the PMBT protocol doing here, is that to kind of randomize a deterministic primitive, which is difficult, very difficult. And it is very difficult to get CCA, quote unquote, type of security from those type of primitives. Maybe to start with, the oblivious PRF was not the right primitive. And the second thing is that when the maliciousness of the adversary is in, the focus of the protocol, then maybe letting the client to decide the tag that needs to be signed is not a great idea. Maybe they need to be jointly computed between the client and server. So identifying these two things, then we designed our protocol differently with a stronger security notion, with an access to the validity oracle, as opposed to PMBT. So this is what anonymous tokens with hidden metadata with ATHM in short does. So we have an EVE interface without the artificial algorithm, verify algorithm. We will only rely on read bit. And then the tag T will be computed jointly by the client and the server. And the most importantly, I think we have here as a result is that we would like to rely on algebraic max instead of the oblivious PRFs, because algebraic max already takes care of the client's maliciousness. And as far as we know, this is the first time that such a primitive is going to be used in this context. So, and this will, these choices that we made in the first 3 bullets will have us, give us the stronger security notions that we would like to achieve. So as I mentioned, the interface will not change too much. The change is that there is no tag T input anymore. It is going to be output from the algorithm. And then there is no verifier. The read bit algorithm is enough to have the validity notion. So now how the PMB notion changes is as follows. We will have some kind of, we will use the similar oracles, but we will introduce a new one, validity oracle, as follows. So there is a flag which is set to false to start with, and it will become clear why we need this. The all-sign query oracle is the same as before. The adversary can query with the input bit B and the query itself. to get a response. And there is a notion of now validity, which means that the adversary can go with the token T and sigma, and then it gets a return, it gets a response which says that either read bit returned a bit or it was an error. So now if we also introduced the oracle, which is essentially going to return the read bit. What is the response from the read bit, depending on the flag being on or off. So this is essentially, if you're familiar with this concept, like this is a CCA1 or lunchtime attacks kind of security. So this is why we have this. We have introduced this flag over here. And in the challenge query, similarly, we will look at the flag. If it is not on, it will generate the responses with the challenge bit, and there will be only one-time access to this challenge oracle. So. Now I would like to switch to the protocol itself. The protocol actually is that it's going to use an algebraic MAC from a previous work from 2018. The MAC is going to have some like triplets of secret keys, X, Y, Z, and the input to the MAC is, let's say, B and T. And the algorithm is just generating, picking a random group element and then multiplying this group element with the scholars, with this scholar here, which is computed with the secret key of the MAC and the input message. And in our protocol in ATHM, this B and T are going to be the attributes added by both the server and the client. So the protocol looks as follows. Now we have the secret key as XYZ, a triplet, and the bit B, and only a public part of the public. It's actually a little bit weird, but the Z is computed with the small z, the secret key of the server multiplied by the generator G, and this is the only thing that will be given to the client. The other part, the capital X and capital Y, will not be given. It's hidden, and the client will start the client query by actually randomly picking the tag, the part of the tag by himself, TC, and then it will just use a mask to mask the TC from the server. And then it will send this T to the server. T will pick its own part of the tag, which is called TS, and then it computes this U and V values, which is going to be at the end returned as a MAC in the client side, and the proof. And the proof is just to indicate that the U and V are computed as described in the protocol, and the B, which is embedded here as an attribute, is essentially a bit. It's no more than 1 bit. So given that a UV pair and the pi and the TS, now the client can finalize the tokens by first re-randomizing the U and V, by also unmasking, and then computing a T, which is computing a tag T, which is the TC and the addition of TC and TS, which are jointly computed by the server and the client here. And there's an ugly formula here that verifies that this is essentially what we will obtain at the end with the P and Q. But the read bit operation is much simpler. There are 2 multiplications the server will do. The server will decide if it is going to be the bit 1 or 0 by checking if this equation is satisfied by either B, or it will return an error. So the security, we formally prove the security of this protocol under the generic group models and the ROM for all the security and privacy notions we had. We also implemented our results. And we compared like the number of multiplications that each of these protocols have, like the privacy, PAS, PMBT, and ATHM. The ATHM is essentially just 3 times more multiplications than the privacy PAS over here, and a little bit better than the PMBT. So when we implemented it in a typical machine, typical laptop, we can obtain some good numbers with hardware acceleration, which is under 1 millisecond. For one round of communication, and this already shows better results than the PMBT because of the less multiplication already, and also the acceleration, the hardware acceleration we allowed in the implementations, which PMBT I think didn't do. So we have the full version available on ePrint. I didn't talk about everything that all the extension and every results that we have, but we have the extended version of the protocols. We didn't want to rely on, for instance, the generic group models, and we can do some more elaborate stuff with the security proofs under DDH, but it introduced some overheads, so it is more the complexity gets higher. And we also showed how to integrate the public metadata in the if you want to integrate public metadata in this anonymous tokens, because the algebraic max that we were using was allowing us to add as many attributes as we wanted. And our code is available in GitHub repository in here. And for the future research that we didn't prove or we didn't look into in this current paper is that if it is possible to prove the security of ATHM without the generic group models, as it is as I described, not the extended versions. And the other I think currently ongoing work on this space is that it is very interesting for people to see public verifiable versions of this, because it was completely symmetric key primitive. And we don't know how to, we can use some kind of pairing mechanisms to convert it into publicly verifiable version, but it is, I think the standardization bodies or the community in general is very interested in designing some publicly verifiable anonymous tokens without the pairing. So these are the open questions that we left as a future work. So, thank you.
Thank you, Betul. We have time for a couple of questions, maybe.
Hi, very nice talk. I guess I have a question more about like how these types of primitives are used. So Privacy Pass was introduced in the context of Tor, where users are actually not tracked at all. So basically the goal was to limit the number of times users had to access CAPTCHAs without actually tracking their identity or anything like this. And this type of system actually assumes that user's identity is tracked, but like at the time where I guess tokens are issued. So do you mind talking about kind of that distance a little bit?
Right, sure. I don't think we can say like, okay, I don't know why I cannot go back, but so yeah, there's no identity requirement during the issuance of the token. As I mentioned, there are some statistical algorithms that you can use on the server side, and these algorithms could be really just looking at the operating systems version or the browser version or something that is not identifying information, and see if this fits into some distribution that they already have in the server side. So it's not always the case that, of course, it is one way to do that, identifying during the issuance, and then during the redemption, completely making it anonymous, and it is kind of unlinkable up to some network attacks or the timing attacks. But currently in the fraud teams or in the security teams who are trying to use those systems, it's not always the case to use the identity. So one application to use those type of primitives is actually click fraud. Like if you can get some information about the client's devices, sometimes even device attestation. I'm not sure how reliable those attestations are, but in the click fraud or to prevent some DDoS attacks, because the client can hoard a lot of tokens, those tokens, and if it doesn't know what bit is embedded inside each token in general, that kind of helps the server to stop those attacks to start with.
Can I make one more point? But the number of bits you embed allows
just one bit.
Okay.
Just
Okay,
one
so
bit. There is no, otherwise it wouldn't be unlinkable. So
Okay.
I think I get this question before. Like even one bit, embedding one bit, the server still can, isolate some part of the word from the rest. But the assumption here is that there is a big tension between the privacy and the security, and we really want to provide privacy, but not to sacrifice the security. So I think logical assumption here was that the server will behave honestly in the sense that it won't try to isolate some part of the community with the embedding bit 0 and the rest differently. So the assumption is kind of the server is a little bit trusted in the protocol, following the protocol.
All right, thank you so much for the discussion. Time is up, so other questions will be taken offline.